Hello. So today we'll be studying refrigerant compressor. So this chapter is basically for knowing the details about the compressor used in vapor compression refrigerant. So you must have studied in the vapor compression chapters and all the next multi-component and multi-evaporator chapter that compressors are very essential in vapor compression system. So we'll go in detail in this chapter. So basically, compressors are those machines which increases the pressure of refrigerant from the low pressure side to the high pressure side. That is the pressure of the vapor refrigerant leaving the evaporator is raised to the pressure that is corresponding to the saturation pressure of the condenser, or actually so it may be it should be higher than the saturation pressure of the condenser or cooling medium, so that the refrigerant will be condensed at the saturation temperature. Okay, so if you have here, suppose let's say the refrigerant is having condensation temperature of 35 degrees Celsius at 5 bar, then definitely your compressor has to and your ambient is at so let's say 36, so you need to definitely go a pressure above your 5 bar, that is around 6 or 7 bar, where your saturation temperature will be somewhere around let's say 30-35 like that, so that it can radiate heat to the ambient. Okay, so if your delta T or temperature efficiency is there, then only your heat transfer will be happening. Okay, so as compressor is a device which will be consuming external work done. So generally your electricity is used for to run the motor, and that motor is coupled with the compressor, so which compresses the refrigerant. Okay, so now we'll be going to the different classification of compressors. So as you can see, so these are different types of compressors according to different criteria. So according to method of compression, okay, this is basically, what is the moving part inside the compressor. So depending on that, your compressor can be classified into reciprocating compressor, rotary compressor, or centrifugal compressor. Okay, and so depending on the sorry, this is a typographical mistake. This is according to the nature of your prime mover or the driving unit of the compressor. So this will be either direct drive or a belt drive compressor. So number of working strokes, whether it is single acting or double acting, it is basically related to your reciprocating compressor. So okay, this is basically repeated. So number of stages, so it may be single cylinder or multi-cylinder or double stage. So again, one of the important factor is whether it is semi-hermetic compressor or hermetic compressor. What is mean by semi-hermetic or hermetic compressor? Basically, the refrigerant is a very high density, and the pressure where you are operating is very, very less. So there is chance of leakage of refrigerant to the ambient. And again, these are very environmental degrading gases. So they need to be confined to the space. So the compressor and the driving unit, all these are incorporated in a single housing, which is very sealed from the ambient. Okay, so that is called semi-hermetic compression. So that is called hermetic compressor, basically hermetic. So semi-hermetic means your direct drive motor and compressor they are in separate unit. Okay, so in your hermetic compressor, all the things, your direct drive or motor and compressor are both in single unit. So then it is called hermetic compression. Semi-hermetic when you have your driving unit at outside. Okay, so these are different types of compressor according to your different classifying criteria. So these are various terms related to your compressor. Suction pressure, naturally this will be the inlet pressure to the compressor, or in case of vapor compression refrigeration, the pressure at the evaporator, that is P1 on the lowest side. Okay, that will be a suction pressure. The discharge pressure will be the condenser pressure, or this is the pressure at which the refrigerant is discharged into the condenser. Okay, so the compression ratio is the ratio between the discharge pressure and the suction pressure. So it is always more than one because your condenser pressure is always higher than your evaporator pressure. Basically, it may be 2, 3, 5 like that. So suction volume, the volume of refrigerant sucked by the compressor during the suction stroke. Piston displacement or stroke volume. So in case of reciprocating compressor, there is a piston which reciprocates to and fro, or like in your IC engine. So it is similar to the compression stroke of the IC engine. So in that case, what is the volume of the stroke of the piston? That is a volume covered by the stroke of the piston. That is called your stroke volume. So mathematically, it is like volume of a cylinder. That is pi by 4 d square is the area into length is the volume. Okay, so it will be unit will be in metric cube. So this is the diameter of the cylinder. So L is the length of the piston stroke. So compressor capacity, this is basically the volume of refrigerant passing through the compressor per unit time or suction volume. Okay. So what is the volume of refrigerant sucked in through the suction stroke? Okay, or per cycle of the per cycle you can say. Okay, per cycle of refrigeration. So what is the volume of refrigerant handle? So volumetric efficiency is the ratio of actual volume sucked divided by the total capacity, or it is the stroke volume of the in case of your refrigerant reciprocating compressor. So this is actual volume handle divided by the capacity of the compressor. Okay, so this is the volumetric efficiency of the compressors. Now I'll go to detail of the reciprocating compressor. So as I already told you that reciprocating compressor is similar to your IC engine. That is, it will have a cylinder. Okay, it will have a cylinder and it will have a piston. So there is connecting rod, there is crankshaft. So once the crankshaft rotates by the prime mover, so it will be rotating at certain speed. So due to the rotation, this piston will now move upward and downward. Okay, so once it moves downward, it will suck air from the, it will suck the refrigerant from the evaporator side. Okay, and then the inlet valve will open at that condition. So okay, so suction will be happening while the piston moves from TDC to PDC. That is from top dead center to bottom dead center. Okay, as again it moves to the next round, or you can say from this position to the other 180-degree rotation of the crankshaft, even the piston will move in the upward direction. Then your inlet valve will be closed like this one. Okay, so once its piston reaches the bottom dead center, then your compression stroke happens. So now piston will be moving from bottom dead center to towards the top dead center. So where your exhaust valve will be opening. So this gives the compression or increases the pressure of the refrigerant. Okay. So compression is achieved by reciprocating motion of the piston used for refrigerants with low volume per kg and the higher differential pressure. That is for 717, that is ammonia, R12 and R40. So low volume means it will have less specific volume so that the size will be less. Okay, so because it is having very motion uh, moving parts, so piston will be heavier. So for less volume applications, reciprocating compressors are used. So available in single acting and vertical and double acting horizontal. That is, this is single acting vertical, and double acting will be like this will be rotated in the horizontal direction, and it will have the suction and compression. So one side, if it is suction is happening, the other side suction will be compression will be there. Okay, so it will be cylinder will be like this. So your piston will be in the middle. So here a cylinder, this is a cylinder. So this is called double acting. Okay, so this is that will be double acting cylinder, suction stroke and compression stroke. Suction valve is opening during suction stroke and discharge valve is closed. Suction and discharge is completed in one revolution or two strokes of the piston. Now, one movement of the from top to bottom dead center is called one stroke. So in two strokes, here one is suction, another is compression. So in one revolution, per revolution of the crankshaft, your one suction and one compression strokes are completed. Okay, so these are low capacity compressors, and are air cooled, and higher capacity are oil cooled. If it is higher capacity, then naturally your lots of movements are there, so which needs lubrication and cooling, so that are oil cooled. The volume between the cylinder top and the top dead position of piston is called clearance volume, like this one. So if this is your top position, this volume, okay, so it is not mentioned here. So this volume between the, so you can see, so this is the this volume, okay. This volume is the clearance volume, okay. So this volume is the clearance volume. So similar to your IC engines if you have studied, okay. So now we go to different or the power consumed or work done in the compression process. So if we are not considering the clearance volume, so the clearance volume is very, very less. So if we are not considering it, what will be the theoretical work done or the energy work consumption during compression? Okay. So it will depend on the what kind of process it is carrying out. So as you see, so on PV diagram, so this is P axis, this is V axis. So here, this is the suction point V to C. Okay. Now this is high volume and low pressure. Now compression will be happening. So volume will be less and pressure will be high. So AB is your suction stroke, this is compression, and this is delivery part. So you have no clearance volume. Okay. So now if you, in this BC process, which is compression, it may be following a curve that will be isothermal or polytropic or isentropic. Okay. So for your isothermal, your PV is equal to constant. That is n PV to the power n. That polytropic index is equal to 1. And for polytropic, it is like anything 1.4 or like that. So for isentropic, it will have certain value 1.4. So any other value, if it will be there between 1 and 1.4, so this will be this. Okay. So let us do the calculation. So as you know from thermodynamics, that area occupied by the PV diagram will give you the work done. Okay. This is basically in your TH diagram. What will be the curve like? Okay. So this is P1 line. This is P2 line. Okay. Or your A, B, and BC, A, B, and CD are this one, and your isothermal will be temperature will be constant, polytropic this will be curved one, isotropic in your S will be constant. Okay, so if the process for isothermal, what will be the work? Now what work done will be the area A, V, C, and D. Okay, so for isothermal, this is the curve A, B, C1, and D. Okay, A, B, C1, and D. So that will be equal to area of C1 dA dash C1 dash, or you can say, so this is the bottom area plus your this area, okay, my, sorry, this area, or you can say D C1, okay, now A dash and B dash. So this total area minus this area will give you, okay, so C1 A1 A dash and C1 dash. So this area needs to be subtracted also. Oh, sorry, this area and this area. Sorry, I'll be annotating so that it will be better. Okay. Now the first one, C1D, C1D A dash and C1 dash. So this is the first one. Okay. It is saying now your second one B C1 dash B. So second one is this one, it is saying. Okay. This one minus, sorry, this is confusing. Okay, it is Now first one is your C1 D A dash and C1 dash. Okay, so first one is this one. Okay, plus B C1. Okay, C1 B dash. Okay, sorry, the annotation. Sorry, just a minute. Okay, now this one is this one. Now next one is this one. Okay, so this one is this one, and your third one is this one. Okay, so it will give you the final value, this one. Okay, so this red one plus blue one, sorry, yellow one minus here this one. So this will give you finally the volume, this one. Okay, all this volume in blue, so this will be the work done. Okay, so sorry for the delay. Okay, so this will be W3, whatever that may be. Okay, so that is equal to, so what happened, first one is your P2 V2. How will see? So here also you can see, so this is like P2 V2. Okay, so this area. Okay, the second one is the work done for a isothermal process, and minus this rectangle is P1, this is P1, this length is V1. Okay, so this rectangle is P1 into V1, this is P2 height, length is V2. Okay, so this is the area under an isothermal curve. So this will give you the final work done. So P2 V2 are similar because it is isothermal process, so PV is equal to constant. So this is cancelled, so only isothermal process रहेगा. So again, similarly for polytropic process, if the process is polytropic, that is BC. Okay, similarly the area will be divided. Now this one is PV, this one is P2 V2. Similarly, the bottom rectangle is P1 V1. The middle one will be for polytropic process having polytropic index n. Okay, so now solving this one, so final value will be like this. Okay, so it is n divided by n minus 1 into P1 V1 into this one. So again, we are simplifying this, we can get, so n by n1 into mr T2 minus T1. Okay, so this is the expression for polytropic process. Similarly, for isentropic process, your n value will be gamma. So this can be derived. This is Cp by Cp is equal to gamma. So Cp minus Cp is equal to R. So you can calculate R if you know gamma and Cp. So this you must have studied in thermodynamics. Okay, so this is nothing but same thing. So you are putting your R value in terms of your Cp value. So this is the power required to drive the compressor. That is, if your work done is known. So work done is the amount of energy consumed per cycle. Okay. So if you have n number of revolutions in per minute. Okay. So for n revolutions, the total amount of work done will be n into W. Now it is in per minute. So divided by 60 means per second. So that will be giving rise to your watts. So for single acting, your n will be n, but for double acting, both side your compression and suction and compression is happening. So it will be 2n. Okay. So this is work done in case of reciprocating compressor when we are considering the clearance volume. So this is a so this V2 is your P2 V2, but we have certain volume where your discharge is stopping. Okay, so this is this volume, or V3 is the clearance volume. Okay, so similarly, this will be the expansion process of the clearance volume gas which is stored at the end of discharge. Okay, so this is the expansion process. This is the compression process. There will be an expansion. Okay, so what happens here? This amount of work is produced. Okay, this which is gas is there, which gas remains in the clearance volume, that forces a piston. Okay, so that extra amount of work we are getting, so it needs to be get subtracted from the work consumed. Okay, so this is nothing but your work done in a polytropic process. Okay, so in the first case we are assuming that the polytropic index for this compression process and expansion process both are same, it is n. Okay, so now here the compression process 1 to 2, so p1 v1 p2 p1. Okay, now value is n minus n, but your p3 and p4 we are applying. Okay, so now p3 is equal to p2 and p4 is equal to p1. So you're taking common this factor, so this minus 1, but here p1 v1 minus p4 v4. Okay, but however this is the actual volume of gas sucked. Okay, because you have in your suction stroke, this is the volume of refrigerant handle. Okay, so this will be equal to the P1 V1 minus 4 will be equal to MRT, which is the M is the mass of refrigerant handle. Okay, so T1 will be here, or this V1 V4 will be the stroke volume of the refrigerant. Okay, so if your polytropic index of compression and expansion will be different, then this will be the expression, because this is the for compression part, this is the expansion part, and we are subtracting both. These values are to be calculated differently because your coefficients are different, sorry, indexes are different. Okay, now your volumetric efficiency of reciprocating compressor, sorry, so volumetric efficiency of the reciprocating compressor we need to know. So this NV is will be equal to the suction volume of actual volume sucked during the suction stroke divided by the stroke volume. So that is V1 minus V4 divided by V1 minus clearance volume. So total volume minus clearance volume. So if you express in terms of your P and V, okay, having polytropic index N, so here assuming that N is same for compression and expansion. Okay, so sorry, this is the for expansion part. So your P3 V3N, P3 V3N is equal to P4 V4N. Okay, so now V4 will be equal to Vc into like this. So you're putting here. So this is the expression by exploiting. So finally, this will be the value of volumetric efficiency in terms of your C, which is nothing but your clearance factor, or Vc divided by V1 minus Vc, or Vc clearance volume divided by stroke volume. So this is what is the advantage of hermetic sealed compression. The leakage will be prevented, less noisy because all the things will be occupied in the single space. Space required is very less. Lubrication is easy. Maintenance is not easy. It is the disadvantage because all the things will be in a sealed chamber, so you need to open it. So your entire plant or compression system needs to be shut down. Separate pump is required for charging, because once you open the compression, then there will be leakage. So separate vacuum pump will be needed for charging and discharging. Okay, thank you. So next we'll be studying the uh, rotary compressors.